So we're going to do a talar spatial frame lab. And so what I wanted to do was spend about 7 to 10 minutes going through a little bit of a background on TSF and deformity correction of the tibia, and then spend about another 7 to 10 minutes going through the slides of the lab. And that'll be the extent of the didactic stuff. And then we'll get you to your lab stations and go forth from there. And then we have lab instructors, and so I think there'll be a lot of hands-on learning. So the indications for tibial deformity correction are malunions, non-unions, supramalleolar bone loss, and altered malleolar relationships. And we're gonna look at a case like this. You know, this is the type of clinical patient. This patient has a recurvatum deformity of the distal tibia, post-traumatic, and you can analyze the deformity by drawing your distal mechanical axis, your proximal mechanical axis. The intersection point gives you your coral location, and you can see in this particular patient the front view did not have a significant amount of deformity, and the patient also has a leg length discrepancy. And so by using the TSF to gradually correct the deformity with an opening wedge correction, you can see the new bone in the triangular fashion, and then it is allowed to heal during the consolidation, and this is the end result. A more complicated example that kind of takes this the step further is a patient who has a oblique plane deformity. So this patient has varus deformity and has recurvatum deformity. Okay? This is not two deformities, it's one deformity, but in TSF language it's actually two deformities. And so this is what it looks like clinically, the varus, and then the frame here is used to create both components of the deformity, to correct both components of the deformity, both the coronal plane and the sagittal plane, and that's all happening simultaneously. And this is the end result. So the TSF is basically like a global positioning device. And I guess by a show of hands within this group, how many people have actually put on TSFs and have some understanding of really what TSF language is and stuff like that? Okay, so it's a bit of a mixed group in that respect. So let me go over some of the basics. And so within the frame, you can think of the frame as being like a GPS system, and you can think of a hinge point within the frame as a virtual hinge in space around which the deformity is corrected. And this is a picture that basically shows how TSF frames can be equivalent to old-fashioned Irizarry frames, and where here there's an actual hinge built into the frame, here the hinge is virtual. And of course these are translation frames. This is called a juxta-articular hinge, which means the hinge is actually outside the frame, and this is a rotational frame showing that you're going to correct the rotational components. But it doesn't require building this sort of complex type of hinge type of apparatus, because you can sort of build in this virtual hinge correction into the system. So there are three components of this, and one of it is terminology, and the other is using a computer program, and the other is using the frame. And you sort of put it all together. When you talk about the deformity correction, there are frame parameters that have to be put in, there are mounting parameters, and there are deformity parameters. And this is some of the nomenclature, and we're going to go through that. And then you put all this stuff into the magic machine, and out come the numbers. And the numbers then give you your correction. So when we talk about planes, the 6 deformity parameters, they are as follows. In the coronal plane, the sagittal plane, and in the axial plane, so in the 3 major planes, there are angulations and translations, and that equals 6, 2, 4, 6. So this is varus valgus and medial lateral translation. In the sagittal plane, your angulation is procurvatum, recurvatum, and your translations are AP translations. And in the axial plane, your angulation is internal-external rotation, and your translation is short and long. And so those are the 6 components of the deformity. And so this illustrates how you would calculate your magnitude of deformity. This is the certain number of degrees of valgus that you have. This is the certain number of degrees of apex anterior or procravatum that you have. And then there's a certain number of degrees of axial angulation. And you're going to put that into the program. Translation is the other part to it, right? You're going to have to say that this point is translated X number of millimeters away from this point, and this point is translated X number of millimeters away. And so these are called origins, and these are called corresponding points. We often refer to the origin as sort of the virtual hinge, if you will, the virtual hinge in space. And then you plug it into the computer program, and you're going to get some feedback. The computer program will allow you to put in exactly the stuff we talked about: AP angulation, translation, lateral view, axial view. So those are those 6 deformity parameters we talked about. You put it in, you get a stick figure feedback, so you know if you're putting it in reasonably correctly. The next big thing is the mounting parameters. This virtual hinge in space that we're talking about has to be defined based on a certain location. And so one of the rings is called the reference ring, and that reference ring is sort of the measuring ground from which you will measure your virtual hinge. So in this example, this ring is the reference ring, okay? And so the virtual hinge, we want to put at that spot. So the way it's defined is relative to the center of the ring. So relative to the center of the ring on the AP view, relative to the center of the ring on the lateral view, and on the axial view. So the center of the ring here is in line with the origin, and you want to place it orthogonal to the reference fragment. So this will be 0 because it's right in line. The center of this ring is X number of millimeters anterior to this. So in TSF language, what you'll end up saying is the origin is 12 millimeters posterior to the center of the ring. And then you're going to put in how many millimeters it is offset in this plane. And so you'll put in that the ring is 30 or 50 millimeters proximal or distal to the origin. So that's kind of the stuff that you'll have to put into the program, and again, we're going to go over that stuff. And then this is the kind of feedback you'll get. You're going to input that data into the computer. This is the kind of feedback you get that shows that you're going in the right direction. Then you put in your struts are mounted between the 2 rings, and you put in that data, the strut numbers, and then you will actually see a diagram of your frame matching the deformity on the stick figure. And it should look reasonably consistent with the frame that you have in front of you, the front view, the side view, etc. Then there's something called structure at risk, and that has to do with how quickly you move the system. The idea here is that, generally speaking, when you're correcting a deformity, there is a certain point that you want to move not more than 1 millimeter per day. And it's usually like at the concavity of the deformity, or it might be the nerve. The point is that it's defined relative to the origin. The origin is that virtual hinge. And so if the point is here, then you will say that the structure at risk is X number of millimeters lateral to the origin. If you choose, and this is where the surgeon gets to choose what you think is an important point to make a structure at risk, then here you would say that it's the nerve is X number of millimeters lateral and X number of millimeters proximal to the origin. And then you'll put this into the program. You'll push a button, and poof, there comes your schedule. The schedule then is your starting struts, your ending struts, and the number of days in between the speed of your correction. So you take a frame that looks like that, and you will make something like that. Now, if there's some residual deformity, you can then run another schedule from whatever residual deformity you have. Another quick example, varus, big varus deformity, procravatum deformity. And so you apply a frame to match your deformity, right? It's going to rotate around the virtual hinge in space, and after about 6 weeks of corrections, you can see that you get a nice correction of deformity and excellent radiographic results. And this really is one of my first TSF cases a number of years back, and it gives you that kind of precision. And you know, there's a potential error at every point in the process. The more accurate you are with your deformity planning, the more accurate you are with your frame placement, your input of the parameters, the more accurate everything is going to be. Okay, so that's part one. The other thing that I would like to do is now take you through the lab. I think the best thing to do is, if there are some pressing questions after the lab, I can answer, but I think maybe the best thing to do is be to jump right in and sort of ask questions as we're going along. So this is the lab that you're going to do, and I would like to start off by thanking our company sponsorship and for setting this up for us. This particular bone has a varus and apex posterior and rotational deformity, and it's at the mid-distal third of the tibia. So we're going to make the distal ring the reference ring. Okay, that's sort of the logical thing to do because it's going to be closer to the deformity. And so we're going to start off by putting a transverse wire in parallel to the ankle, and that's going to be your first ring. You're going to attach a 155 millimeter ring to that, and you're going to secure it with wire fixation bolts and tensioning, and so you're going to get exposed to all of that. And that, by having that ring parallel to the ankle, you're going to ensure that you're perpendicular to the distal mechanical axis in the coronal plane. That's a given. You've just got it with that one wire. Now, your second point of fixation is going to determine whether you're parallel to the mechanical axis in the sagittal plane as well. So you can then attach a 3-hole Rancho cube at the off of the superior part of the ring, and you're going to insert a half pin. And by doing that, you are going to ensure that you're going to make sure that the ring is perpendicular to the axis in the side view as well, on the lateral x-ray as well. And then there's also, the third step is going to be to insert a tibiofibular wire, which is going to go from posterolateral to anteromedial, and that's going to get inserted with, it's going to be fixated with wire fixation bolts. So that's going to be your distal fixation. That, in many cases, is enough. If you want some additional fixation on your distal ring, you can add a third wire, which is posteromedial to anterolateral. So this is deluxe fixation: 3 tension wires, multiplanar, and a half pin. That's your distal ring. Now you're going to put your proximal ring on, and I would recommend that you, just a practical thing, put your proximal ring on the bone before you get started, because otherwise you're going to have a hard time getting that ring on. So now you want to put a proximal ring on that's 155 millimeter, also a 155 ring. And the question always is, where do you insert this? And just from a practical point of view, the recommendation is about 17 centimeters proximal to the other ring. That just gives you enough working distance to get the struts on and to make it a comfortable frame. So that's when you're going to plan your proximal ring. And then there are a number of ways to fixate this ring. You can put a wire in first, a perpendicular wire, the same sort of fashion, set the coronal plane, and then put a half pin in, and then set your sagittal plane. Or the other example of what they're showing in this laboratory is that you can start with an A to P half pin, perpendicular, attach it to a cube, and then dial in to make sure it's perpendicular in the frontal plane. I think some of the lab instructors will show you how to do that. Then the laboratory is also showing you the options of having sort of these oblique pins that are going off at various angles. I think that's kind of optional. You don't really have to do that. I guess the important thing here is that this ring is perpendicular to the proximal axis, right, from the front view, from the side view, and you fixate it with 2 half pins or a wire and 2 half pins. Once you do that, you have all of your fixation. And this is called the rings first method. So you have a proximal ring, you have your distal ring, and so your proximal is 2 half pins in a wire or 3 half pins. Your distal ring is 3 crossing multiplanar wires and one half pin. So you put your struts on, and you're going to end up with a situation like this. You're going to have a frame that matches the deformity, right? And this is the point at which you are going to then get ready to do your osteotomy and your correction. But really, before you do all this, this is the time to do your measurements. And the measurements are, you're going to have to input certainly the struts and the frame, the ring sizes. Those are called your frame parameters. But the things that I just went over with you, the 6 deformity parameters, yeah. I mean, I think, honestly, that's going to really be something at the labs. We'll go over master tabs, making sure that the rings are oriented in the perpendicular direction and facing forward. But what you're going to have to input into the computer, and this is what you want to do before you start cutting the bone here, is going to be you're going to input the 6 deformity parameters, which you actually will be able to do with just by taking a goniometer and measuring the angles. You'll measure the angle on the front view, you'll measure the angle on the side view, and you'll look at the axial angle to determine that. That'll be your 6 deformity parameters. You're going to have to measure your mounting parameters, so you're going to have to ask yourself, where is this virtual hinge, this hinge point, the apex of the deformity, the cora, the stuff that you've been hearing over and over again, where is this relative to the reference ring? So these are your deformity parameters. We talked about that. These are going to be your mounting parameters. Now, some tricks for the mounting parameters. In this particular case, we're going to make the distal ring the reference ring. Now, you could make your mounting parameters off of the proximal ring. You have that option. But in general, we use the ring that's closest to the apex of the deformity. So in this ring, we will do this. There are little tricks, and again, I think the lab instructors are going to be most helpful for this, for sort of figuring out where is the center of the ring and how to define the apex, the position of the virtual hinge, also known as the origin, relative to that center ring, front view, side view, and axial distance. And you're going to input that information into the computer. Then you're going to do your osteotomy. You're going to open up your program, and you are going to do the correction gradually, and you're going to see it straighten out. And I think that's going to be very exciting. Any residual deformity that you have at the end of the thing, you'll remeasure, and you can input new deformity parameters in. Like, let's say you do your correction, and at the end of this whole thing, you still have 3 degrees of varus, and let's say you have a little bit of translation. That happens. I guarantee you it's not a problem with the frame or with the program. It's a problem with the way that you've measured. It's a problem with the way you've mounted the frame. The more precise you are, the more precise the end will be. But the beauty of this system is that if you have that residual deformity of 2 or 3 degrees and you have that residual translation deformity, you can re-input that into the program, run another schedule, and you can make it perfect.